All right, let's dive right in. Today, we're talking all about speed, but we're not talking about sports cars or fighter jets. We're talking about speed on the molecular level. Welcome to the world of chemical kinetics, the amazing science of just how fast chemical reactions actually happen.
And right out of the gate, we're faced with a pretty big puzzle. Think about it for a second. An explosion. That's a chemical reaction that's over in, well, a flash. But an iron nail rusting, that's also a chemical reaction, and it can take years, even decades. So what gives? Why this enormous difference in speed? Answering that one question, well, that's the entire point of kinetics.
So here's our game plan for cracking this mystery. First up, we're going to figure out how you even measure the speed of a reaction. Then, we'll decode what's called the rate law. Think of it as a reaction's secret recipe for speed. After that, we'll zoom way in to see the molecular collisions that make it all happen, learn how we can actually control that speed, and finally uncover a reaction's hidden pathway.
Okay, let's jump into part one, the science of speed. How in the world do you put a speedometer on a chemical reaction? Well, it all starts by measuring the pace of the change itself.
You know, it's actually a lot like measuring the speed of a car. A car's speed is just distance over time, right? Well, for chemistry, the reaction rate is simply the change in the amount of something over a certain amount of time. Scientists call that amount concentration. So, more stuff changing in less time, you got it, that's a faster reaction. Pretty straightforward.
Now the cool part is, we can track this in one of two ways. We can either watch how quickly our starting ingredients, the reactants, are getting used up. That's why there's a negative sign there. Their concentration is going down. Or we can watch how quickly our new stuff, the products, are appearing, which is why that has a positive sign. Either way, they both tell us the same thing, how fast this thing is cooking.
And check this out. This is where it gets really clever. The balanced equation itself, those numbers out front, they act like a conversion key between the speeds of everything in the reaction. So if we know that hydrogen, H2, is popping up at a rate of 0.78 m per second, we can just look at the equation. It tells us for every 6 of those hydrogens we only make 1 P4. So the rate of P4 is just 1/6 of hydrogen's rate. A little bit of math, and boom, 0.13 m per second.
All right, let's move to our next big clue. It turns out that reaction speeds aren't random at all. Nope. They follow a very specific mathematical recipe for speed, and it's called the rate law.
So this is the general recipe. Now, don't let the letters scare you. It just says the rate is equal to some constant, K, multiplied by the concentration of your reactants raised to some power. Those little exponents, N and M, that is the secret sauce. They're called the reaction order, and they tell you precisely how sensitive the speed is to each ingredient. And here's the kicker. You can't just look at the balanced equation and guess them. You have to find them through experiments.
So how do scientists actually do that? Well, they put on their detective hats and use a clever strategy called the method of initial rates. The idea is simple, but it's totally brilliant. You just run the reaction a few times, but here's the key. You only change the starting amount of one ingredient at a time. That lets you totally isolate what effect each ingredient has on the overall speed.
Let's do some of that detective work right now. Compare experiments I and I. See how we doubled the amount of reactant A but kept B the same? Now look at the rate. It went from 0.0078 to 0.0156. It exactly doubled. That perfect one-to-one relationship means the reaction is first order for A. Okay, now look at experiments I and 3. This time we doubled reactant B, and what happened? Nothing. The rate didn't even flinch. That means B has zero effect on the speed. We call that zero order.
And just like that, we've cracked the code. Based on the evidence we just gathered, the final recipe for this reaction is rate equals K times A to the first power times B to the 0th power. And as you might remember from math class, anything to the power of 0 is just 1. So the B term basically disappears. Our final recipe is simply rate equals K times the concentration of A. We decoded it!
Okay, so we figured out the how, but what about the why? Why does that recipe even work? To answer that, we have to zoom way, way down to the level of individual molecules and their chaotic little dance. We need to talk about something called collision theory.
So at its core, collision theory is pretty simple. For a reaction to even have a chance of happening, molecules have to physically smash into each other. But here's the thing, just bumping into each other isn't enough. For a collision to be effective, to actually make something happen, it has to pass a 3-point inspection. 1, they have to collide. 2, they have to hit each other with enough energy. And 3, they have to hit each other at just the right angle.
That whole sufficient energy thing, it's so important it gets its own name, activation energy. And the absolute best way to picture this is to imagine a giant energy hill. For your reactants to become products, they literally have to have enough energy to make it up and over the top of this hill. If they don't have enough juice, sorry, no reaction.
And of course, there's a beautiful piece of math that ties this all together. It's called the Arrhenius equation, and it mathematically connects that rate constant, K, from our recipe, the size of that activation energy hill, E, and the temperature, T. This is the master key that shows us exactly how temperature controls reaction speed on a molecular level.
Now this is where it gets really powerful. Because once you understand how collisions and energy hills work, you can stop just being an observer, and you can actually start controlling reactions. We can, for all intents and purposes, hack the rate. So chemists basically have 2 main levers they can pull. The first one is temperature. You crank up the heat, the molecules start zipping around faster, and they crash into each other harder and more often. This means way more of them have enough energy to get over that activation hill. The second lever is a catalyst. A catalyst is like a chemical shortcut. It doesn't give the molecules more energy. Instead, it creates a brand new, easier path for the reaction to follow. It essentially builds a tunnel right through that energy hill.
And that brings us to our final section, the last crucial piece of this entire puzzle. See, most reactions don't just happen in one big, simple step. They actually follow a secret, multi-step pathway to get from start to finish.
This whole series of tiny steps is called the reaction mechanism. It's like the detailed, turn-by-turn directions for how reactants become products. And along this path, you often get these temporary, fleeting molecules called intermediates. They pop into existence in one step and then get totally used up in the very next one. Now, if you remember just one thing about mechanisms, please make it this quote: "A reaction is only as fast as its slowest step." Think about it like an assembly line. It doesn't matter how fast the other workers are. The overall speed of the line is always going to be limited by the slowest person. That slow step is the bottleneck.
And that slowest step, that bottleneck, it has a special name, the rate-determining step. And here's the beautiful, mind-blowing connection that ties everything we've talked about together. The recipe, or the rate law, for that single, slow step has to match the overall experimental rate law that we figured out with all our detective work earlier. It's how all the pieces click into place.
And that brings us right back to where we started, to our original mystery. So why is an explosion so fast and rust so slow? Well, an explosion is a massive concentration of reactants all smashing into each other with incredibly high energy, setting off a lightning-fast chain reaction. Rusting, on the other hand, is this super slow motion process where individual atoms react with low energy, one by one, over a very, very long time. It's the exact same science, just playing out at 2 completely different speeds. So, we've seen how kinetics gives us the amazing power to measure, predict, and even control the world at the molecular level. And that leaves us with one last big question to think about. Now that we have the keys to the very engine of chemistry, what impossible things that might seem like pure science fiction today, like new medicines, self-healing materials, unbelievable technologies, what might just become possible tomorrow?